This is the 5-5 time machine, otherwise known as a free-running oscillator. This circuit produces a square wave alternating between a logic high and a logic low. The output is represented by a LED, which continuously turns off and on, as you can see. A potentiometer is included to control the frequency of the square wave. This project has two parts, the square wave generated with the 5-5 IC and the one without. This is the square wave generated by the 555 IC. It has a duty cycle of approximately 50% and can be adjusted by a potentiometer. The longer the period, the lower the frequency, and the smaller the period, the higher the frequency. This is the pinout diagram of the 555 IC. Pin 1 is wired to ground while pin 8 is wired to V++. Pin 2 is the trigger which begins the square wave. Pin 3 is the output pin. Pin 4 is the reset pin which restarts the output, which will be unused in this circuit. Pin 5 is the voltage control pin, which controls voltage fluctuations between VCC and the output. This is also unused in the circuit. Pin 6 is a threshold pin, which works with the trigger pin to restart the square wave. Pin 7 is the discharge pin, which is connected to the capacitor to allow for continuous discharging and charging. Pin 8 is wired to V+. This is a schematic diagram of the major sections of the 555 IC. This circuit can be divided into three 5K ohm resistors, which is where the name of the IC comes from, an NPN transistor, two op amps, an SR latch / flip-flop, and an output driver with a NOT gate. This video intends to unravel the 555 IC to show how the square wave is generated by the chip. Here is a more in-depth schematic. The circuit will always be in one of two states. Either the LED is off or on. First, as the capacitor charges through these two resistors, 2/3 of VCC will be on this inverting input and 1/3 of VCC on this non-inverting input. This is because the three 5K ohm resistors act as voltage dividers. So 2/3 of VCC is here, 1/3 is here, and 0 volts is here. For the op amp above, since the non-inverting input has a higher voltage level than the inverting input, the output is high. For reference, if the non-inverting input is greater than the inverting input, the output is high. And if the inverting input is higher than the non-inverting input, then the output is low. For the op amp below, the inverting input has more voltage than the non-inverting input, so the output is low. The outputs for the op amp are wired to the SR latch. This is the SR latch created with NOR gates, and it will latch onto its output until the other input is applied. So if I click on this PBNO, the output will not change, and the LED will stay on. This LED will turn on once this button is pressed. This is a truth table for the SR latch. Following this logic, as the reset pin is high and the set pin is low, Q is low and Q bar is high. The output from Q goes to the inverter, outputting a high. Therefore, the LED turns on. However, as the capacitor reaches 2/3 of VCC, the circuit state flips. Instead, 2/3 of VCC is presented on the inverting pin of this upper op amp, which is greater than the non-inverting pin, outputting a low. 2/3 of VCC is presented on this non-inverting pin of the lower op amp, outputting a high. Now the SR latch can reverse its output. The reset pin is low and the set pin is high. This makes the output Q high, resulting in a low output. This would activate the transistor, which offers a path to ground for the capacitor through the discharge connection. The capacitor will discharge until it reaches 1/3 of VCC, repeating the entire process. Demonstration of the circuit in Felsted, showing how the output switches from a high to a low. On the bottom right, the square wave is represented, and on the bottom left, you can see the capacitor charging and discharging between 1/3 and 2/3 of the supply voltage. In conclusion, this project demonstrates the versatility of the 555 chip and how it can be used as a timing pole / oscillator, which has several applications in digital circuitry.